Okay, so this is about ICs. ICs means integrated circuits, and as ICs, what we discuss in our syllabus is op amps actually, right? Op amps, right? So basically, we have open loop configurations, closed loop configurations, right? There are like quite a few things about op amps, right? Okay, so these are the questions from op amps, ICs. First one, a 741 operational amplifier, right? 741, that's the only IC we have in our syllabus, 741, right? 741 operational amplifier, powered with a supply voltage of plus or minus 15 volts. If V1 and V2 represent the input voltages and V out represents the output voltage, the variation of the V out with V1 minus V2 is best represented by, very straightforward, very much straightforward, right? So about we know about an open loop op amp, right? V out is given by, right? V out is given by A times V1 minus V2. A is called A is called open loop voltage gain, right? A is open loop voltage gain, and V1 minus V2 is called differential voltage. V1 minus V2 is called differential voltage. Right, then you asked V out and V1 minus V2, no? Then V out is Y. This is X axis. This is M. So basically its shape is Y equals MX. But any op amp and any kind of an electronic appliance actually, they are reaching their saturated levels. Then that is Y equals MX. That is true. That is Y equals MX. But it should be saturated at the end. So answer is 1. Right? We have plotted this in the theory class also, in the theories. Right? That is 1. That is 1. Y equals mx, but that is not 2 because it is reaching the saturation. Then it is 1. Second one. The operational amplifier circuit shown operates with plus 10 volts and minus 10 volts power supplies. Plus 10 volts and minus 10 volts. Okay. What would be the approximate output voltage of the circuit? Right. Now, one thing you should notice is this is the standard non-inverting. This is the standard non-inverting voltage amplifier. This is standard non-inverting amplifier. Then for that amplification is proved. Amplification and the closed loop voltage gain of that amplifier is a proved equation. That's a proved equation, right? Then first thing you should see is that this is non-inverting voltage amplifier, right? Voltage amplifier, right? Then if this is 0, the other side of the battery is 2, no? This side of the battery is 2, then this is 2, and that voltage is the Vin of our usual op amp. This is called the Vin input voltage, right? Then the proved equation for the circuit is V out of Vin closed loop voltage gain is 1 plus R1 over R2. 1 plus R1 over R2. Then you asked about V out. Just plug these values. V out over Vin is 2. 1 plus R1. R1 is a parallel resistor. R2 is the other resistor. Then 10 over 1. 10 over 1. So this is V out over 2 equals 10 over 1 is 10, then 11. V out equals 22 volts. 22 volts. But the thing is, right, very important. But the thing is, output of any kind of an op amp cannot exceed Vs values. Vs means supply voltage values, right? Output of any kind of an op amp cannot exceed Vs values, right? Now, even though it is supposed to go up to 22, 22 means plus 22. Even though that is supposed to go up to plus 22, it will be cut off at plus 10 because 10 is the maximum supply voltage given. Then answer is not 22, that is 10. Answer is 10, right? Very important. Right? V out of any kind of an op amp, V out, right, is always less than or equal to Vs. V out is always less than or equal to Vs. Then saturated value is also, it should be less than Vs. And if there is an ideal op amp, it goes up to Vs. If there is a normal op amp, normal means if there is a typical ordinary op amp, it is usually 10, it is usually 2 volts less than the supplied voltage, right? Okay. Next, third one. Third one, the voltage gain of the circuit shown is, right? Again, this is the standard non-inverting amplifier, right? Nothing. V out to V in is 1 plus R1 over R2. V out to V in is 1 plus R1 over R2. Closed loop voltage gain is V out to V in. Closed loop voltage gain means V out to V in, then 1 plus R1 R. Then R over R is 1. This is 2. So it is 2. Nothing to do. It is 2. 4. The figure shows an operational amplifier circuit with a light dependent resistor LDR and a 1 kilo ohm resistor. Right. The supply voltage of the operational amplifier is plus or minus 16.5 and its saturation voltage is plus or minus 15. Saturated values are given separately, they are plus or minus 15. Then if this op amp is going to saturate at any point, that is going to go up to plus or minus 15 only. That is going to go up to plus or minus 15 only. The resistance of the LDR is 1 mega ohm at complete darkness. 1 mega ohm at darkness and 100 ohms at bright light. The approximate values of the output voltage of the circuit V out at the complete darkness and the light. Okay. Then V out is asked. Again, this is grounded 0 and this V in is now 1.5. V in is 1.5. This is a standard non-inverting amplifier again. Standard non-inverting amplifier again. Then V out over V in equals 1 plus R1 over R2. Right? Then we need V out. V out is given by V in times 1 plus R1 over R2. Then apply the equation. Then V out. V in is 1.5. 1 plus. Right? First we will do at darkness. Then 1 plus R1 is 1 kilo ohm. 1 over 1 mega ohm. 1 kilo ohm means 10 to the power 3. Right? 1 mega means 10 to the power 6. Right. Then approximately, right, we can say this is, see, V out equals 1.5, 1 plus, right? This is 1 over 1000 means approximately 1, no, right? Because this is 1 over 1000. This is 1 over 1000. 1 plus 1 over 1000 is 1 plus 0.0001, right? Approximately 1, right? Mega 1 over 1000. Then approximately 1, since there is approximately 1, V out is 1.5 volts, right? 1 end is done, 1.5. Then darkness, 1.5. Then we need that light. At light, V out equals V in 1.5, 1 plus 1 over 1 means 1000 ohms, kilo over 100. Then this is 10. Now V out equals 1.5 times 10 means 11, no? 11. 1.5 times 11 is, right, 15, 16.5. 1.5 times 11 is 16.5. But in the saturation, this could go up to the saturated levels plus 15. This could go up to the saturated values only. That is 15. Right? 16.5 it goes up to 15 only. That is the saturated value. Right? Even though it is supposed to go up to 16.5, it stops at 15 saturation. Then 15, 1.5 and 15, 1, right? 1. Right, next. 5. Which of the following curves correctly represents the variation of the voltage gain V out over VI means V in, of the circuit shown when the value of R1 is changed from 1 kilo ohm to infinity? Right. Now again this is the standard non-inverting operational amplifier. See how many times it has repeated. V out over V in equals 1 plus R1 over R2. Now according to this diagram, if I adjust this, V out over VI is 1 plus. Now this is what we refer as R1 usually. This is what we refer as R2 usually. Right, now here they are switched. Then R1 is given as R2. Right, and that is 99. Let's write 99 at once. So that is 99 over R1. Then I need this, no? Just check the ends first. Ends check just check the ends first. R1 is changed from 1 to infinity, no? Then when this is 1, right, maybe when this is 1 kilo ohm, when this is 1 kilo ohm, V out to V in equals, right, when this is 1, 1 plus 99 no 1, that is 100. So the graph starts at 100. Graph starts at 100. Graph starts at 100. Then if you check the end value, V out to V1 equals 1 plus 99 over infinity. Anything over infinity is 0. Anything over infinity is 0. Anything over infinity is 0. Then this goes to 1. This goes to 1. Then it should be a variation from 100 to 1. It should be a variation from 100 to 1. 100 to 1. It cannot be 0. It is varying from 100 to 1. 100 to 1. Then 100 to 1 means it is 1. See how easy? 100 to 1. The answer is 1. Right? 6. 6. The inverting input of a 741 operational amplifier operating with plus or minus 10 volts power supply voltage is provided with a voltage signal which increases linearly with time t. Right. Then this should be, this is V1, our usual notations. Plus terminal is called V1 and the negative terminal is called V2. Negative terminal is called V2. Right. Some says that is V plus and V minus. That's also fine. Right. Then this should be the signal of V2 and this should be the signal of V1, which increases linearly with time. The non-inverting input provided, V plus, non-inverting input terminal is provided with a rectangular voltage waveform of amplitude 5 volts as shown. The output waveform of the operational amplifier is best represented by, right, in open loop configuration, very straightforward. In open loop, in open loop, in open loop, in open loop, right, we know it works from V out equals A, V1 minus V2, right? But the respective theory part is this. Respective theory part is this. When we draw this curve, when we draw this curve, these saturated values of V1 minus V2, right, are very small as much as 150 microvolts and minus 150 microvolts. They are very small values as 150 microvolts. So therefore, when we do calculation sums, what we do is this, right? At once, what we consider is if V1 greater than V2, we consider this as positively saturated. Positively saturated, right? Then if V2 is greater than V1, because that is definitely going to exceed 150 microvolts, no? Then V2 greater than V1, directly we consider it as negatively set. Negatively set, right? That's it. Now check for a few time intervals. Check for few time intervals, right? Same thing. Check for few time intervals. First one, if you check for the first one, right? First time interval, no? First time interval again. V1 is 5 volts, right? V1 is at 5, but V2 is less than 5. In first time interval, V1 is greater than V2. Then it is positively saturated, which means that is called plus V out set. Plus V out set. Plus V out set is equal to Vs in an ideal op amp. Vs is given as operating voltage means supply voltage. 10, no, plus or minus 10, then plus V out set is plus 10. Plus V out set is plus 10. Right? If you check for the second time interval, in second time interval, V1 is 0. V1 is 0. Compared to 0, V2 is greater than 0. Which means in the second time interval, V2 is greater than V1. That is negatively saturated minus V out set. Then the output is minus 10. Minus 10. Alright, if you check for the third again, same as first one. V1 is greater than V2. Positively saturated. Plus 10. If you check for the fourth again, greater than second scenario, right? V2 greater than V1, negatively saturated, minus 10. Then plus 10, minus 10 changes. It swings between plus 10 and minus 10 from time interval to time interval. Simple. Then it swings between plus 10 and minus 10. Then it is 5. It swings between plus 10 and minus 10. Answer is 5. Swings between plus 10 and minus 10. Right? Give me 1 second. 1 second. Right. Right. Next. Question 7. 7. 7. In the given circuit, the 3 7 4 operational amplifiers 1, 2, 3 are operated by power supplies of plus 15, plus or minus 15, plus or minus 10, plus or minus 8. Right? VS. Power supplies means VS values. Respectively, the approximate values of the output voltages V1, V2, and V3. Right. All are open loop, no? If all are open loop, just as the previous question, what you need to check is whether V1 is greater than V2 or, sorry, V2 is greater than V1. Right? Okay, for that, I need potentials here. Now, if this is 8 volts, right? This is at 8 volts, right? This is at 8 volts. If this is 8 volts and if this is 0, right? We know these four are 4 resistors in series combination, no? Because no current flows through input terminals of any op-amp. First golden rule, right? Then therefore, all 4 are in a series combination. If all 4 are in a series combination, their voltage drops are equal. Equal resistors, equal current, then voltages are also equal. Then if there is 8, then we can get the voltages here as 8 volts here, 6 volts here, 4 volts here, 2 volts here, 0 here. Equal voltage drops. That's it, right? Now it's done. Then check for the first one. Check for the first one. What is the first one? Mega. Check for the first one. V1 of first one is at 8. V1 of first one is at 8. V2 of first one is at 6. Then about the first one, right? V1 greater than V2. Then that is positively saturated plus V outset. Plus V outset is plus 15. Plus V outset is plus 15. Right? Then for the second one, if you check, second one is here. V1 is at, sorry, V1 is below. V1 is at here, 0. V1 is at 0. Right, maybe V1 is at 0. And V2 is at 4. V1 is at 0. V1 is at 0. V2 is at 4. Then in that case, V2 is greater than V1, which means that is negatively saturated, minus V out set. Then minus 10. Its operating voltage is 10, no? Supply voltage. Then for the third one, if you check, third one, V2 is taken from 6. And V1 is taken from 2. Then in that also, still V2 is greater than V1, negatively saturated, minus V outset, then minus 8. Then it is plus 15, minus 10, minus 8. It is 2. Right? Easier. 8. Which of the following statement is incorrect? Okay. 1. The electrical conductivity of an intrinsic semiconductor increases with increasing temperature. Electrical conductivity increases, right? in the semiconductor discussion also I explained the same, because in semiconductors, in intrinsic semiconductors, when temperature increases, resistance decreases. When resistance decreases, conductivity increases. One is correct. A full wave rectifier cannot produce a constant DC output voltage for a sinusoidal input. In full wave rectifier, the output is something like this. That is not exactly constant, but it is close to constant. It is something like this, no? Something like this. And if there is a smooth, the current is like this. If there is a smooth, the current is like this. Then after smoothing, what you are getting is something like this. After smoothing, what you are getting is something like this. It is approximately constant, but not exactly constant. Not exactly constant. Then we can consider it as correct. Cannot produce, yeah. Harima straight line, but it is close. It is close. 3. In a bipolar transistor, the emitter is heavily doped than the collector. About doping, doping is about the concentration of electrons. Doping is about the concentration of electrons. Transistors are the cure, right? Then in a transistor, IE, IC, and IB varies this way, no? In the previous one, I explained this. In the previous video, I explained this. IE, IC, IB, IC, IB. Then concentration and doping is same as this. Then higher current means higher doping, higher concentration, higher number of electrons. Then in bipolar transistor, emitter is heavily doped than the collector. Yes, because IE is the highest current. 4. Drain current ID of a junction field effect transistor JFET is maximum when gate source voltage is 0. When gate source voltage is 0. Yes, because we know we know in a JFET, VGS is also, it is always, not also, it is always negative when it operates. It is always negative when it operates, right? If that negativity is less, then current increases. Then transistor maximum when gate source voltage is 0, it is correct. That is maximum when gate source voltage is 0, correct. Because VGS equals VG minus VS. VGS equals VG minus VS. VGS equals VG minus VS, right? Then if VGS is 0, which means VS equals VG, which means VS equals VG. 4 is also correct. 5 is a popular case when an op-amp is used in a voltage comparator. Closed loop set is used. No, that is the open loop. That is not the closed loop, that is the open loop. Voltage comparator circuit is the LDR circuit we discuss usually in the class. LDR circuits, right? The configuration we have in LDR circuits is called the comparator circuit. Right? LDR circuits. Right? LDR circuit means the configuration we had in LDR. මේකට තමයි comparator එක කියලා කියන්නේ. configuration එකට මම උනා දෙන්නම්. Right? The configuration is this. Right? The same thing we had in LDR circuits. Configuration is this. Right? Configuration of the circuit is this. Right? මෙහෙම resistors connect කරලා මේක මෙතෙන්ට connect කරලා, then here there are 2 resistors again. Right? This configuration, this is called the voltage comparator. Right? This is called the voltage comparator. This is called a voltage comparator circuit. Right? There is an open loop. Output is not connected back to input terminals. There is an open loop. There is an open loop. 5 is wrong. Right? 9. The figure shows 3 circuits ABC made of identical op-amps. All 3 circuits are fed by identical input voltage Vin from an ideal voltage source. Which of the following correctly gives the comparison of the respective magnitudes of the output voltages VA, VB, and VC of the circuits? Okay, again a simple scenario, and the given case is a popular case again. That's a non-inverting voltage amplifier. Now, for nth time we are writing here V out of Vin equals 1 plus R1 over R2. For the non-inverting amplifier, V out of Vin equals 1 plus R1 over R2. Now, V out is given by V in times 1 plus R1 over R2. Now, in this case, V in is given as V in is same, no? It says all 3 circuits are fed by identical V in. Then V out varies with voltage gain 1 plus R1 over R2. Apply this for these 3 scenarios given. Then for first one, VA is proportional to 1 plus R1 over R2 means 40 over 10. 40 over 10 is 4, then that is 5. Then for the second one, VB proportional to, right, 1 plus, that is also 40 over 10. That is also 40 over 10. Right? This one is not needed because that is inactive. No current flows through V in. No current flows through V in. Then this is also 5. Then VC, these two are working as R1 together. 40 plus 10 is 50 over 10. So that is 5 plus 1, 6. Then VC is the highest. VA and VB are equal. VC is the highest and VA and VB are equal. Right? It's 2. It's 2. Right? So that's the end of op-amps. That's the end of op-amp questions. Right? Okay, then we'll meet with logic gates in the next video. Right?